Hi everyone, welcome to PrepFusion. So we are going to start our new chapter now that will be semiconductor junctions. Sir, what is the meaning of junction that we need to understand, and mainly in this particular chapter we will study about PN junction only. Sir, what do you mean by PN junction? So everything we will see, but we will build up our concept from where we left. We left at the semiconductors. We saw uniformly doped semiconductor, we saw non-uniformly doped semiconductor. Okay, so we will start from there only. Now some people would be thinking that sir, I already know the concept of uniformly doped n-type semiconductor. I already know everything, but still you should not be skipping this part. Here in this particular part, whatever that we are revisiting, in that particular part as well, I will be telling some new things. Okay, so those new things you need to learn. So don't skip it. You can watch it in a quicker manner, but don't skip this particular part, because from here only the concept of PN junction would be made up. Okay, so we have studied this uniformly doped n-type semiconductor. What was the Venn diagram for this one? This was at equilibrium. What do you mean by uniformly doped? The doping has been done uniform. From x equals to 0 to x equals to L, the doping is uniform, right? So what kind of energy band diagram you were getting? Sir, very simple. I was having EC, valence band, and in between I was having intrinsic Fermi level. And sir, since it is n-type semiconductor, so our Fermi level would be nearer to conduction band. So conduction band, valence band, intrinsic Fermi level, and EFN, right? And sir, when I applied an external bias, what really happened? Sir, here positive voltage came into action, here negative voltage came into action. Whatever the electrons that were at x equals to 0, electrons at x equals to 0, so their energy went down, and here negative into negative, their energy went up. So this kind of diagram we were getting. So sir, this we have already studied, and sir, I already know that EC, EV and EFI, EC, EV and EFI would always have the same phase. Whatever the look EC would be having, the same look EC, EV and EFI would have. Along with that, sir, there is some current flowing as well. So there is some current flowing as well. So that's why there would be a slope in EFM as well. Here there was no slope in EC, no slope in EFN, no slope in EFI and no slope in EV. Why is that so? Because sir, there was no current and no electric field. What did I tell you? Electric field would be 1 by Q dEC by dx. Here you can see that there is a slope. And what is the direction of electric field? Sir, the direction of electric field is this one. This is the direction of electric field. So in the direction of electric field, the slope of EC would be positive. So in the direction of electric field, the slope of EC is positive. So this is also I told you, right? So this was your E external. All good. Along with that, I told you the current would be proportional to the slope of Fermi level. Note this Fermi level. This intrinsic Fermi level is of no use. In this chapter, I will be rarely making this intrinsic Fermi level. Okay. This is of no use, but our main Fermi level is this one, which is coming because of n-type semiconductor. So here in this n-type semiconductor, the slope of Fermi level would be representing the current. So if there is some current, that means there would be some slope as well. And in the direction of current, the slope of EFN would be positive. So this we have already studied. Then we studied about non-uniformly doped n-type semiconductor. So in non-uniformly doped n-type semiconductor, what was the scenario? Sir, this is the scenario. Again, it is open circuit only. Sir, one particular part is highly doped and one particular part is moderately doped or lightly doped. So this part is highly doped, this part is lightly doped. So the part which is highly doped, that can be represented as N plus, and the part which is lightly doped, that I am representing with N. Is that clear to you? N plus means highly doped, N means lightly doped. So what will happen? Sir, because of the concentration gradient, here there are more electrons, here there are lesser electrons. What electrons would do? Electrons will try to move from left to right. Right? These electrons will try to move from left to right because there is a concentration gradient. Our tendency or the tendency of electrons would always be that we will always move from higher concentration to lower concentration. Same goes for holes as well, from higher concentration to lower concentration. Right? So since they are moving, then what will happen? Sir, here positive would be maintained, and sir, here a lot of negative charges would be there. And because of that, sir, there will be one electric field build up. That electric field we called as E built in. Or you can say, sir, there is some potential build up here. That potential we were calling as V built in. Right? Now this electric field, what this electric field would do? Sir, this electric field would make sure that if a lot of electrons are moving here, then this particular electric field would put this kind of force on the electrons. So electrons would be drifting in this particular direction and they would be diffusing in this particular direction. So this was your, initially electrons were diffusing in this direction, so this was your electron diffuse. I am moving a bit faster because this we have already understood. And electrons are drifting in this direction, so this is your electron drift. Since electrons are drifting in this direction, because of the drift, the current direction would have been this. So this is your I drift. And since they are diffusing in this direction, so this would have been your I diffusion. And at the equilibrium, I drift would be equals to I diffusion, and the total current would have been 0. And it is pretty obvious as well, because this is the semiconductor which is having no external bias. If there is no external bias, that means it is under equilibrium. And under equilibrium, there has to be 0 current. So current is 0, but there has been an electric field that has been built up, that is E built in. So what kind of energy band diagram we were making? So this kind of energy band diagram we were making. There would be a slope in EC. Why is that so? Because this particular part is positively charged and this particular part is negatively charged, and because of the positive charge on the electrons, their energy is going down, and because of the negative charge on the electrons, their energy is going up. So this side energy is going up, this side energy is going down, right? Or how you can think, sir, this is the direction of built-in electric field. So in the direction of built-in electric field, the slope of EC has to be positive. In the direction of built-in electric field, the slope of EC has to be positive. So in this manner as well, you can understand. Now one thing you know that, sir, current is 0. Sir, since current is 0, so there will be no slope in EFM, right? There will be no slope in EFM. And what about EV, sir? EV would look similar to EC only. EV would always look similar to EC only, and same goes for EFI as well, but I don't need to make EFI, okay? I am not making EFI here. But there is something wrong in this diagram. What is wrong, that we will see later on, okay? There is something wrong in this diagram. Can anyone think of it? What is wrong? What did I tell you? That your electric field would be this relation. Electric field is equals to 1 by dEC by dx, right? So can I directly write down that electric field? Here electric field I am denoting by capital E, but it should be denoted by small e. Like not small e, this kind of E. So I know one thing, that electric field is proportional to dEcx. Your EC is a function of x, no? Like here EC value is low, here EC value is high. So it is a function of x divided by dx, right? Now, if I am saying that the slope of EC is uniform, like if you are making this kind of EC waveform, energy versus x you are drawing, and this you are saying that this is my EC. That means you are saying that ECx is linear. It could be, sir, some 3x plus 5. So this could be the expression of ECx. And if you differentiate it, what do you get? 3. That means you are saying that, sir, this built-in electric field, it will be a uniform value. But when we solve the numerical, I got to know that this built-in electric field was not a certain numerical value. It was coming out to be a function of x as well. Are you understanding this point? Here, if I am making this diagram, right? If I am making this diagram, what I am saying? Sir, dEc by dx is uniform. It will be a constant value. Or I should say it will be a uniform value. If it is a uniform value, that means my built-in electric field should also be uniform. But when I solve the numerical problems, I got to know that built-in electric field was actually a function of x, and it is pretty obvious as well. No, why it is obvious? You consider this particular structure, okay? You consider this particular structure. If I go to this electron and I ask him, do you see concentration gradient? What I am doing? I am going to this electron and I am asking him, do you see concentration gradient? What he will say? Sir, here I see one electron. Sir, downward I see one electron. Sir, here also I see one electron. So basically, sir, I am not seeing much of concentration gradient, although this electron knows that if he looks ahead, then there are no electrons here. Although this electron knows that, sir, there is concentration gradient, but near me, there is very less concentration gradient. But if I go to this particular electron, what this electron would say? That, sir, if I look ahead, no electrons. If I look this side, no electrons. Sir, there are very lesser electrons. If I look downward, then there is an electron. But sir, I am surely seeing some concentration gradient. Basically, this particular electron would see more concentration gradient than this particular electron. That means which electron would be more tending to diffuse? Which electron will diffuse more fastly? this electron will diffuse more fastly or this electron will diffuse more fastly. Who has more tendency to diffuse? This particular electron will have the more tendency to diffuse, no? Are you able to understand this point? Because this particular electron is seeing more concentration gradient. So what will happen? This was your scenario. Now this particular scenario, this donor atom, what it would do, this would leave its electron very fastly. I should not say very fastly, basically this particular electron would have more tendency to diffuse. That means this would become a positive ion, and surely here there will be some negative ion because of the holes. So here the electric field would be built up. So more tendency of electric field to be built up is there in this particular region. Although here also some electric field could be built up. Here also in the whole scenario some electric field will be built up. But the important part is that electric field will not be uniform. Surely at the junction, this is known as junction only, because after this the scenario is changing, no? Before this uniform doping, after this uniform doping. But here at the junction, at the midpoint, the scenario is changing. From n plus 2 we are moving to n. From n plus 2 we are moving to n. N plus 2 n. So where the scenario is changing, at the junction you will get maximum electric field. Do you agree to this point or not? Without mathematics we are able to understand this particular point. Just by the pure intuition, that this particular electron will have more tendency to move than this particular electrons. That means this will make stronger electric field here. So here if I am making this particular diagram, what does that mean? I am saying that, sir, electric field is constant. This particular diagram I am making with respect to x, right? This particular part was x equals to 0. I hope you haven't forgot. Like this particular part I used to call x equals to 0, and this particular part I used to call x equals to L. So I was saying that from x equals to 0 to x equals to L, I am having a uniform electric field, which statement was absolutely wrong. So there is some problem in this diagram. That problem I have told, right? So how we are going to eradicate this problem, how we are going to move from here to the actual diagram, that I am going to tell now. But before that we can see one more case. Right, all this is fine, this also I can remove. So in short you can write down that this is having some problem, but this problem will be eradicated later on. Okay, now in this particular diagram what was the scenario? First, this particular semiconductor that was in equilibrium. In equilibrium what was the scenario? That some built-in electric field has been set up here, right? This built-in electric field has been set up here. Now what you are doing, you are applying an external bias. Because of this external bias, what will happen? There will be another field that will be set up. There will be another field that will be set up across the semiconductor. That field will be EB, right? So this particular field will be EB. Now this EB is actually supporting EBI. What was the role of this EBI? What was the role of this EBI? This EBI that was set up, what was the role of this EBI? That if some electron will try to diffuse from here to here, then what this EBI would do? This was trying to go from here to here. This EBI will put the opposite force. This electron was trying to diffuse from here to here. EBI will say move back. Electron will say I want to diffuse because of the concentration gradient, but EBI will say move back. Now what is the scenario? You have made EBI more stronger. Another external bias you applied, that EBI has become more stronger. So now what this EBI would do? It has been become more stronger. So the electron that tried to diffuse from here to here, now he will not be able to diffuse more. Why is that? So previously only he was not able to diffuse, now as well. Now that tendency of diffusing has become even weaker. But because of this higher electric field, what will happen? Because of this higher electric field, what will happen? That this particular electron which was here, now the drift would increase. Are you able to understand this point? Do you remember this particular scenario? We made the diagrams and then I told you that diffusion would depend on Q dn dnx by dx. Now diffusion almost remains the same, but because of the higher electric field, what will happen? The drift would increase. So here what will happen? The drift would increase, right? Although this is not important, but directly I will make the diagram. Here what I would do, sir, EB plus EBI, that means electric field has become stronger. So this slope would become even more stronger. This particular slope would become even more stronger, right? Here I was having this much of slope. Here I would have even more slope. But again, this diagram is not completely correct. Why is that so? It is partially correct only because here you are saying that sir, slope is uniform. If slope is uniform, that means electric field should be at all the points electric field should be uniform, but it is not the scenario. Electric field is not uniform. Here at the junction you would get a more electric field, but at these points the electric field would be lesser, right? So EC. Now there would be a current as well. What will be the direction of current? Sir, electron tried to diffuse from here to here, and electron tried to drift from here to here. This was the drift, this was the drift, and this was the diffusion. Now sir, because of this applied electric field, the drift has been much more stronger. The diffusion is, you can say as it is, but drift has been much more stronger. Why drift is stronger? Drift is stronger because of this electric field. This external electric field is making this drift stronger, and if this drift is stronger, then what will happen? The electron would be drifting in this direction, and if they are drifting in this direction, that means there will be some drift current that would be set up. So in this particular direction, drift current would be set up, and I told you a very simple way that whatever the direction of battery is there, based on that you can understand what will be the direction of current. If you don't want to think this much diffusion, drift, if you don't want to think in this direction, what you can simply say, so battery direction is this one, so from battery always the current would get out. So current would always get out from here. Or what you can see, sir, diffusion and drift were equal under the equilibrium. Now what you have done, you have made drift stronger. Why drift stronger? Because E built in and EB, they are supporting each other. They are in the same direction. So if the drift has been becoming stronger, that means electron would be drifting much more now. So because of that, the drift current would be more than the diffusion current. So eventually drift and diffusion were cancelling out each other, but now the drift has become even more stronger, and because of that the final current would be because of that drift, right? And if electrons are drifting in this direction, that means the current would be in this direction. So what will be the direction of current? This would be the direction of current. So all these points we have already discussed, just we are revising and we are getting to know that what was wrong there, right? What was wrong? The wrong was that, sir, this is how the diagram should not have been made, because you are saying that, what you are saying? Sir, you are saying that EC is, the slope in EC is uniform, that means your electric field would be uniform, okay, which is not the correct case. Now I want to ask you another question. What I want to ask, let's just say this is 5 volt, okay, so how this 5 volt will be dropped down across the semiconductor? What I am asking, I am saying that, sir, VB is 5 volt, and I am saying that this is 0 volt. If this is 0 volt, then surely this will be 5 volt, right? So let's remove this EB for now. This EBI I am making here, okay. So what I am saying, this is 5 volt, this is 0 volt. Now how this 5 volt and 0 volt will be dropped down? This is what you need to comment. Like, will it be dropping down equally? Like 5 volt, then here 4 volt, then sir here 3 volt, then sir here 2 volt, then here 1 volt, and then sir 0 volt. Will it be dropping down equally? No. Why is that so? What did I tell you? That this particular electron has more tendency to leave, right? This particular electron will have more tendency to leave. This particular electron will have more tendency to leave. But this particular electron will not have tendency to leave. So eventually what kind of scenario you will be getting? Sir, here plus 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 has been made, and here plus with electron, plus with electron, plus with electron, plus with electron, plus with electron. And I told you in semiconductor, who is responsible for the current? Who is responsible for the current? These electrons, these movable electrons. These electrons can move. So these movable electrons are responsible for the current. Now what is happening here? You are only getting the charge. This positive charge will not move, no. Who will move? Electrons will move. This positive charge will not move. That means in this particular region, what you have done? At the junction, what you have done? At the junction, you would see that the number of electrons which are present, that are very, very less. The number of electrons which are present, the number of movable electrons which are present, that has been gone. Because of that, this particular region will have more resistivity. Like if charge carriers are present, that means n value is high. What is the value of sigma? Sigma is n q mu. So if charge carriers are present, then n is good enough. If n is good enough, that means sigma is good enough. If sigma is good enough, that means J equals to sigma, current would be good enough. Basically, if sigma is good enough, then resistivity, what is the resistivity? Resistivity is rho, that is 1 by sigma. If sigma is good enough, that means resistivity will be low. That means this particular part is having lesser resistance and this particular part is having more resistance. Why is that so? Because this particular part has lost its movable electron and eventually it has become only plus 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 plus. And since it has lost its movable electron, that means its resistivity has become higher. So what does that mean? If I make the equivalent diagram, can I make it in this manner? That here there will be lesser resistance, but here there will be much more resistance, and here as well there will be lesser resistance. Why is that so? Because the important part would be happening at the junction only. Are you able to understand this point? The important part would be happening at the junction only. This will say, sir, I don't see much of concentration gradient. Why is that so? Because he can see that one electron is there. He can also see that one electron is there. But what he will see, sir, 3 electrons are there. I can see this electron as well. I can see this electron as well. Sir, I can see this electron as well. Right? Are you able to understand this point? Okay. So more electrons from here would come this side. They will not be reaching towards till this side, but most of the electrons would be reaching here only. Are you able to understand this point? Right? And all these things we will see in our PN junction as well. But as of now, what did you understand? That at the junction, there is high resistivity. So because of that, this 5 volt will not be dropped equally. Most of the 5 volt will be dropped at the junction only. 4.9 will be dropped here only. So if this is 5, this will be 4. Or let's call it 4.8. So if this is 5, this will be 4.9, and if this is 0, this will be 0.1. So you are getting 4.9 minus 0.1, 4.8 volt here. So at the junction, from this VB, most of the potential will be dropped at the junction only, because at the junction you are having very high resistivity. Why you are having very high resistivity? Because at the junction the movable charge carriers are gone, the movable electrons are gone. This was having some electron, this was having some electron, but this guy has lost all its electron. Right? So this VB will also not be dropped equally. Most of the part of VB will be dropped at the junction only. Are you able to understand these points? Okay. From here only all the concept of PN junction has been built up. Okay. But directly we start from PN junction, and that's why sometimes we find PN junction as a tougher topic. But we will build up all the concept here. When we move to PN junction, you would realize that it is simply a piece of cake. Okay. So this diagram we have made. Now let's understand these particular scenario by some other sense. What kind of sense? So what I am doing, I am picking one N plus semiconductor and one N semiconductor. Both are same material. Basically, I had a silicon semiconductor, same material was there. What I did more doping here. But I did lesser doping here. So this is also N type, this is also N type. Right? But here there is more doping, here there is lesser doping. So that's why I am calling this one as N plus, this one as N. So I am calling this is N plus type of semiconductor and this is N type of semiconductor. Okay. So can I make the energy band diagram for them? Surely I can make the energy band diagram for them. How can I make the energy band diagram? Sir, EC, EV. Sir, EC, EV. Sir, why this gap is same? Why this gap is same? Because they are made from same material. Same material means they will be having same band gap. EC minus EV represent band gap only, no? So they are made from same material. So they will be having same band gap. Right? Now where would the EFI come into action? It would be right in between. Okay. So here would be your EFI. Now I will make EFN now. Right? Fermi level I will make. So this is more highly doped. That means EFN would be closer to EC, right? More doping means more closer to EC. These much basics you already know. And lesser lesser doping means far from EC. Although it is N type only, that's why the EFN, the Fermi level would be on the upper part of intrinsic Fermi level, that's for sure. But here there is more doping. That's why this EFN is here, and here there is lesser doping, that's why this EFN is here. Do you understand this gap? This gap is lesser. That means it is showing more doping, and this gap is more. that means it is showing more doping. Here also you can verify the same thing. Less gap here, more doping. More gap here, lesser doping, right? Now if I join them, okay, what I do, I join them. I join them in this manner. I have joined them. Now one thing I know, that eventually this semiconductor would get into equilibrium. Eventually this semiconductor would get into equilibrium. At equilibrium what will happen, that I don't know. Although I know what will happen at the equilibrium, but as of now let's consider that, sir, I have joined both of them. What will happen at the equilibrium I don't know, but I know one thing, that at the equilibrium current has to be 0, because there is no external bias, so current has to be 0. If the current has to be 0, what does that mean? That means this EFN plus and this EFN has to be flat. Are you able to understand this point, what I am saying? When I joined them together, I know that, sir, I don't know anything, but I know that current would be 0. At the equilibrium, current would be 0. If the current is 0, that means if I make the Venn diagram, then whatever the Fermi level I make, that has to be flat. Whatever the Fermi level that I make, that has to be flat. What does that mean? If you want to make the energy band diagram for this one, then the Fermi level has to be flat. So what you can do in this diagram, that this part goes up downward and this part goes upward. This EFN plus goes downward, this is your EFN plus, this is your EF. This part goes downward and this part goes upward, then they would come together. Are you able to understand this point? EFN plus goes downward, EFN goes upward, so they would come together. That means this part need to come downward and this part need to go upward. So what will happen? This EC would go upward and this EC would come downward. So if you make the diagram, how it would look like? So this EC has gone upward and this EC has come downward. And eventually what you can see, sir, EFN has become flat. I hope you are able to visualize this particular thing. I should not write down EFN, I am simply putting EF, because if I write down EFM, then people will think that this did not move, only this guy moved. But actually both are moving, right? This one is going upward, this one is going downward, because I know that the Fermi level has to be flat. So I am simply putting EF. Similar thing would be happening with EV as well, but you don't need to think of EV. Why is that so? Because you know that whatever the structure EC is having, the same structure EV would have. So I don't need to think much about I don't need to think much about EFI and EV, because I know that they will follow the same structure as EC. So we are only talking about EC now. We are only considering about EC now. So what really happened? These guys move upward and this guy went downward. So I will simply make two arrows in this manner, that this one moved, this one moved downward and this one moved upward. So EC went above. Here also, like, both were at the same level previously, because both were made from the same semiconductor material, no? So both were at the same level previously. But now what really happened? This has went upward, this has went downward. Now you know one thing, when I go from x equals to 0 to x equals to L, okay, when I go from x equals to 0 to x equals to L, I know that my electron concentration is decreasing. If electron concentration is decreasing, what does that mean? That means the gap between EC and EF should rise up. Basically, you need to join these lines. Are you able to understand this point? And when you walk through this particular scenario, what do you see? This gap is continuously increasing. This gap is continuously increasing. What does that mean? That means your electron concentration is decreasing. If this gap increases, that means electron concentration is decreasing. Are you able to understand this point? Very simple point. Very, very straightforward. If the gap between EC and EF is more, that means your electron concentration is less. So why I joined them? This is the main target. Why I joined them? I joined them because I know that when I move from here to here, this gap should rise up, which is rising up as well. So I joined them in this manner. Sometimes in books, what you will find out? In books, you will find out that they have joined like this. But if I join like this, there is some error. What is the error? What do you think? The same error that we discussed. What is the error if I join by a straight line? If I join by a straight line, the problem is that you are saying that built-in electric field will be uniform. But is your built-in electric field uniform? No. That is a function of x, because more built-in electric field you will get here. Are you able to understand this point? So this is how I should join them. Okay, and when you find out the slope, you will see that at the junction you will get the maximum slope. Why at the junction you will get the maximum slope? Because you know that at the junction you will have the maximum E field, maximum electric field. So whatever the kind of structure of EC you are getting, the same kind of structure of EFI you would get, and the same kind of structure of EV you would get. What I do is that I will simply copy it. Okay. I don't need to make EFI, so I'm not making EFI. Okay. Now let's see more things. What all more things we can see from here? But this gap is looking lesser now, so it doesn't look good. Basically, both are N-type only, no? So the gap between EF and EV would be more only. What I mean to say is that this gap would always be more than this gap, no? Right? So this gap should look larger only. Although this gap would be very, very larger. This particular gap would be very, very larger. Right? But anyway, this gap, and if you compare this gap, so this gap would always be lesser. Why is that so? Because both are N-type. Although this is highly doped, that's why this gap is very less, and this is lightly doped. But both are N-type only, no? So they can never be closer to EV. Here also this gap has to be more only. That's why I made this diagram. Now more things we can see. So the correct way of representing the diagram would be like this, not like this. So in the examination, if the diagram is coming for this particular diagram, then the diagram would be made in this manner, not in this manner. In the worst case, if it is made in this manner as well, what you would do, you will click on the correct answer. That's why this is correct. But actually, it will be made in this manner only, not in this particular manner. Is that clear to you? Okay. And why I made them flat here? Nearly they will be flat. Why nearly flat? Because you know that here the electric field, the built-in electric field will be very, very less. Why it would be very, very less? Because you know that the tendency of leaving the electron is very less here. Because this is not seeing much of concentration gradient. Although he knows that there will be concentration gradient, but if you just look here, then there is not much concentration gradient. And if there is not much concentration gradient, then tendency of leaving the electron is very less here. So that's why I made it nearly flat, and then this kind of slope I was getting. Okay. Now more things I can see. On this side there is more electrons, no? This is your x equals to 0, and this is your x equals to L. So here there is more electrons, and here there is less electrons. Yeah, that's fine. Okay. The built-in electric field is in this direction. Now you let me know, if electron wants to move from here to here, the electron wants to go uphill. The electron wants to go uphill. So what could be the motivation to go uphill? Diffusion. Whenever electrons wants to move uphill, the motivation is diffusion. And whenever the electron wants to go downhill, the motivation is drift. What I actually mean to say is that if you are standing here, and if I push you, if I just give you some push, what will be happening? You will be rolling down, right? If you are standing here, and if I give you a light push, will you be reaching here? No. If you are standing here, and if I give you light push, will you be reaching here? No. But if you are standing here, and I just give you a light push, what will happen? You will roll down. It might happen that, sir, the push was not very strong, so I reached till this point only. But what I am saying is that with respect to the applied electric field, if I am applying an electric field in this direction, or you can say this is built-in electric field only, which has been come up from the material only. So if there is an electric field in this direction, what does that mean? That means you are putting the force on electron in this direction. So these electrons will move from uphill to downhill because of the external force. But this external force will not make them move from here to here. Right? Basically, if you are standing here and I am pushing you this side, basically this electric field, what is the meaning of this electric field? The meaning of this electric field is that force on electron will be on this side. So if you are standing here and I am pushing you this side, what does that mean? That means I am stopping you to go to the uphill. So this particular electric field is making them come downward, and this particular electric field is stopping them to go uphill. But there is some motivation to go uphill. What is that motivation? That motivation is diffusion. Like here there are more number of people and here there are lesser people. So what do you think? Sir, I don't want to settle down here. Where you will be settling down? You will be settling down in Delhi or you will be settling down in Manali? Where you would want to settle down? Where there is less crowd. So motivation for these guys is diffusion because there is lesser crowd. Always we want to diffuse from lesser crowd to, from more crowd to lesser crowd. So from more electron density to lesser electron density, they want to diffuse. So this is the diffusion. But what is the force here? People from Manali also want to settle in Delhi. Why is that so? Because in Delhi you will get better facilities, right? There will be better hospitals, there will be better schools. So there is some force which is making them go downward. That is drift. Because of the drift they want to go here, and because of the crowding they want to go from downward to upward. So did you understand my point? This I am telling for electrons. For holes it will be completely opposite. Holes will try to, they can move from here to here because of the drift. Like whatever the process that happens in electrons, the opposite process happens in holes. This I have already told, right? So electrons will move from, holes. What about the holes? If I talk about holes here, so here there are lesser holes and here there are more holes. Although this is n-type semiconductor, but in n-type semiconductor as well there will be some holes, no? So if there are lesser electrons, that means there are good amount of holes, and if there is more electrons, that means there are lesser holes. Although the number of electrons in this side would be more than the number of holes only, but if I compare, here there will be lesser holes and here there will be more holes, right? So if electron wants to move downward, then what is the motivation? The motivation is diffusion. And if they want to move upward, then what is the motivation? Motivation is drift, because built-in electric field is in this direction. So what this built-in electric field would do? Built-in electric field would force the electrons, it would force the holes to go upward. So are you able to understand this point? I am writing down one conclusion. What is the conclusion? That I am writing for electrons. For holes it will be completely opposite. We will not think in the direction of holes, we will always think in the direction of electrons. So what I am saying, for electrons, downward I can write down, downward motion means drift, and upward motion means diffusion. Now under the equilibrium, what is happening? Let's remove all these guys. Okay, so under the equilibrium, what is the scenario? The same number of guys are moving upward and the same number of guys are moving downward. So concentration here and here remains same. Basically the same number of guys are moving upward, that means the same number of electrons are diffusing and the same number of electrons are drifting as well. That means drift and diffusion current is same, and drift and diffusion current is same. What does that mean? Total current is zero, and that's why this particular condition is known as equilibrium condition, right? So motivation to move upward for electrons, that would be diffusion, right? Why is that so? Because of the concentration gradient. And motivation to move downward, just a little force would make them move downward. So that would be drift. Because of the electric field, you are moving downward. Is that clear to you? And here in this scenario, drift and diffusion are equal to each other. Now what do? I apply an electric field. What do? This scenario I have already understood. So this was the scenario. This was flat. So they were joined together. The same structure I got here. So this was flat only. Now if I apply an electric field which is in this direction, I am applying this electric field which is in this direction. So what do you think what will happen now? If I am applying an electric field which is in this direction, what does that mean? Positive multiply with negative, that means their energy would go down, and negative multiply with negative, their energy would go up. So the same diagram, what it will happen? This particular part would go up, this particular part would go up, and this particular part would go downward, right? What will happen if I apply an electric field? Then this particular part would go up and this particular part would go downward. So what kind of diagram you will be getting? Sir, whatever the barrier that I was having, that barrier has increased now. So here only this much barrier was there. What this barrier is known as, we will talk about it. Although you already know the name, but we will talk about this particular barrier. So sir, this barrier will be increased now. So this particular barrier would be increased. So this particular barrier has been increased now, sir. Okay. And another thing that would happen is that, sir, now current is also not a 0. So will I make the current diagram like this? What do you think? Like, should I make the current diagram in this manner? Not current diagram. Should I make EFN in this manner? That's the EFN should be made like this. Is that correct? If I say I current is flowing here, then how much current would be flowing here? Sir, I only. Here also, sir, I only. Here also, sir, I only. Here also, sir, I only. So everywhere the same current is flowing. So ideally, how I should make my EFN? What did I say? And this is a function of x as well. Current is same, no? So ideally, this is how it should be made. Okay, but even in the examination, if it is made in this manner as well, then also it is fine. Okay, but I will make in this manner. In the examination, if it is made in this manner or sir in this manner, you would click on this that is correct. But ideally, current would be same only, no? So I would make down in this particular manner. Okay, and same goes for EV as well. But here the important part to understand, one important part we are understanding here, what we are understanding. Just join it. Yeah. So what we are understanding, that this barrier has increased now. This barrier has increased. Previously, this barrier was, this is known as built-in potential only. Sir, why it is known as built-in potential? We will discuss that. But now this barrier has become V built-in plus VB. Because whatever the built-in potential that was set up here, this particular electric field is supporting this built-in potential, right? So I should not make by arrow because potential is simply a potential only. So I should not be making it with arrow, but I should make it with plus minus. So this plus minus is being added with plus minus. That means both are supporting each other. So this barrier has increased. You can understand by the simple concept of energy band diagram as well, or you can simply say that in the direction of built-in potential only we are applying some VB. So this barrier has increased now. Now you will just let me know one thing. Here there were more electrons, right? Here there were more electrons, and here there were lesser electrons. Which process has become simpler now? Diffusion or drift? Let's just say in this scenario you are standing here, and in this scenario you are standing here. Now I am applying a force of 1 Newton on you, like I am pushing you by the force of 1 Newton. And here also I am pushing you by the force of 1 Newton. Where you will roll more? In which condition your rolling will be more? Like when you reach here, in both of the conditions, let's just say you are reaching here. When you reach here, in which condition your velocity will be more? In this condition, no? In this condition, right? Why in this condition? Because sir, here the slope is more, no? The slope is more. That means I will be moving faster. Or you can say that, sir, here the electric field has increased. The applied electric field has increased. That means you are putting more force on me. But the barrier has increased now, sir. Barrier has increased. Sir, this particular barrier has increased. When this was the barrier, even with this barrier, not a lot of electrons were able to move. Now, sir, the barrier has increased now. If it is increased, then sir, going from here to here, the probability has reduced even more. Previously, at least one electron was moving here. But here, sir, even one electron would not be able to move. Previously, what was the scenario? One was moving here and one was coming downward. So drift and diffusion were same. But now what is the scenario? So 2 would come downward, but 0 would move upward. That means drift has increased. And did we discuss the same thing here? The same thing we discussed here. The drift current would be increased. Because electric field has been set up more. Previously, whatever the diffusion was there, that diffusion also had become a bit lesser. Along with that, the drift has increased more. So this current is dominated by drift. Here what was the scenario? Drift was equals to diffusion. But here what is the scenario? The drift is more than diffusion. So this current was dominated by drift. You see here, you can understand by the analogy as well that if I am pushing you from here to here, you would be able to move faster. That means more electric field is there, more force you will feel. Even if I am applying a force of 1 Newton, here also I am applying a force of 1 Newton, but here you would feel, sir, you have put more force because I would be rolling more here. But sir, here I would be rolling less. So here what was the scenario? The amount of electrons that was diffusing and the amount of electrons that were drifting, both were same. But here you have made diffusion even lesser because you have increased the barrier. So increased barrier would reduce down the motion, would reduce down the diffusion. So this particular scenario is drift dominant. Are you able to understand this point or not? Like we understood the scenario, we understood the same kind of scenario in basic semiconductor physics as well. We are understanding the same scenario with this particular diagram as well. And now we are understanding the same scenario with the simple energy band diagram as well. So with respect to formula, with respect to energy diagram, with respect to physical meaning, from every single thing you can understand your semiconductor physics. Are you able to understand this point? Sir, why you are teaching all these points? The topic name was PN junction. Everything would come up, but believe me guys, if you have studied this particular part from n plus to n, then PN junction would be simply a cakewalk. I will be explaining there, but there you would say that, sir, I already know everything. Okay, here what we are doing, n plus and n, no. There what we will do, this side will be p, this side will be n. So here there will be more number of holes, here there will be more number of electrons. That means if there are more electrons, there will be lesser holes. So here there will be more number of holes, there will be lesser number of holes. Here there will be more number of electrons, there will be lesser number of electrons. So PN junction is nothing but it came from the concept of n plus and n. So what I am telling you here, that without a bias, this was the condition. When I applied the bias, I have increased the drift. Now if I apply the opposite bias, in this manner, this was the scenario that we already discussed, right? This is your equilibrium. Equilibrium we have already discussed. So here this was your barrier. Now what I do, I apply the electric field. This was the VB. Now I have interchanged the polarity, right? So now previously what was the scenario? Sir, VBI was set up in this manner. Now VB I am setting up in this manner. Why I am making most of the VB here? Because you know that most of the part would be lying across near the junction only, right? Near the junction only most of the part would be applied. So that's why I am making VB not like this. VB I should have made by this, but I know that most of the part of VB would be dropped across this particular junction only. So that's why I am making VB like this. Now this VBI is opposing this VB, but we will not understand in this scenario. We will understand by energy band diagram. So what does your energy band diagram say? Let me make it more better. So now what this energy band diagram would say, that sir, negative potential is applied here, positive potential is applied here. Sir, positive potential multiply with electrons. So sir, this energy would go down. And sir, here negative multiply with negative, their energy would go up. So now what will happen? Sir, these guys would go up and these guys would come downward, right? Negative multiply with negative, positive. That means here the energy is becoming more. So positive multiply with positive. Sorry, positive multiply with negative. Here the energy is becoming lesser. So this part is becoming downward, this part is coming upward. So what does that mean? The gap between this EC, and the gap between this EC. So previously if the gap was VBI, now the gap has reduced to VBI minus VB. Are you able to understand this point? The gap has been reduced now. This gap has become VBI minus VB, right? So along with that, what you would see, there will be a current that would be set up in this direction, right? So current would be set up in this direction. Basically what you can see is that this part is going downward, no? So this EFN is going downward and this EFN is going upward. So this kind of current you will be getting, right? What I am saying is that, so this EFN is going downward and this EFN is going upward. So what do you see? This kind of scenario would see. This kind of scenario would see, right? So here I should write EF, not EFN, because people will be getting confused that, sir, this EFN and this EFN is same. So here I am writing down EFN, here I am writing down EFN plus. Okay, so that you don't get confused. Here only I am putting EF, only I am putting EF. And you know that picture of EC and EV would be same only. Right, but always make sure one thing, that this gap is looking lesser, which is not correct. So this gap should always be more. Okay, this gap should always be more. So what do you think, this current would be dominated by diffusion or drift? The current that you are getting in this scenario, that would be motivated or dominated by diffusion or drift. Sir, in this scenario we were not able to diffuse. Sir, in this scenario we were not able to diffuse, or whatever the diffusion we were getting, the same drift we were getting. But now, sir, barrier has reduced now. So now I can diffuse more. But if you are standing here and you are standing here, if I give you a force of 1 Newton, if I give you a force of 1 Newton, in which scenario you would feel more force? Sir, in this scenario I would feel more force, because the slope is more, no? Like if I am standing on flat surface and I push you, then you would feel that, sir, I did not feel much force. But if we are on a slanted surface and if I push you, then you would roll down more. So similarly here, the effective electric field has reduced down. The effective electric field, although electric field is still in this direction, what I am assuming is that this VB is lesser. Okay, VB is not that high. So if electric field is still in this direction, right? The electric field that I am saying, that is still in this direction, but that electric field has reduced now. This electric field has reduced now. So because of the electric field, very less electrons are moving. But because of the diffusion, more electrons would move, because previously they were not able to climb up. But now they will be able to climb up, because the slope has become lower. So here there were, basically what I would do is that I would take this scenario here. Okay, so previously they were not able to climb up, but here these more number of electrons, they will be able to climb up more. And if they are able to climb up more, then what will happen? They will be moving in this direction, and since they are moving in this direction, so current would be set up in this direction. So more diffusion would be there. Although some electrons will still be moving here. Some electrons, let's just say 1 electron is moving here, but 3 holes will be diffusing here. If 1 electron is moving here, that means drift current would be in this direction. But this drift current would be lesser, but more electrons are diffusing. That means more diffusion current would be there. So this is your drift and this is your diffusion. So diffusion would be more than the drift. So total current would be flowing in this direction, and which we can directly see that this is the direction of current. Okay, not able to make in correct manner, but you can see that, or from the battery as well, you can see that, sir, this will be the direction of current. So in the semiconductor, current is flowing like this. So are you able to understand the depth? Right? Diffusion, drift. Drift is lesser, diffusion is more. So what I would say, this is diffusion. Here what I write down? Yeah, drift dominant. So here I will write down diffusion dominant. Now the question would come up, sir, why you are doing all these things? So remember the first lecture. In the first lecture, what did I say? Why we are using semiconductors? Sir, we are using semiconductor to become controlling. What we need to do? We need to control. I want to be controlling. Controlling for a human being? No. Controlling for current. Sir, I want to be controlling. So first scenario what we studied, that, sir, by doping you can control. Sir, there was intrinsic semiconductor that was having very lesser current. So, sir, you did the doping. When you did the doping of p-type and type, you were able to get more current. So, sir, by doping you can control. So, first thing is already studied. Now, second thing is, sir, if you have done the doping, that means you have made a particular device, no? Let's just say this fan is running at a speed of 4. Now, I want to run this fan at a speed of 5. So, will you say buy a new fan? Right? This is not the criteria, no? Using this fan only, you need to control the current. So using the same material only, using the same semiconductor only, I need to control the current. If I was using this kind of semiconductor, uniformly doped semiconductor, then whether you apply the electric field in this direction or you change the electric field. Let's just say if I had applied the electric field in this direction as well. Previously I am applying electric field in this direction. So whatever the current that I am getting, that is same. If I interchange the polarity, then also the current would be same only, no, just the direction would change. But the amount of current remains the same only. I am just telling why we are studying all this topic, why we actually study PN junction. Because we want to be controlling. First controlling we did with the doping. Now you know that again and again, sir, I cannot change doping. Let's just say at a particular scenario, I'm getting 2 milliampere of current. Now someone says that, sir, I need 0.5 milliampere of current. So what you will say? Change the doping. Here you are doping 10 to the power 16 atoms. Now you dope 10 to the power 14 atoms and you will get this much of current. Which is not a good way, no? Because device has been already fabricated. You cannot change the device. So what did you get to know? That from uniformly doped semiconductor, sir, I cannot achieve anything good, right? From uniformly doped semiconductor, sir, I am not able to achieve anything productive. Then I went to non-uniformly doped semiconductor, N plus and N. Sir, when I am changing the bias, here I am applying this kind of biasing and here I am applying this kind of biasing. Sir, with respect to changing the bias, what I can see? In one of the scenario, my current is becoming diffusion dominant. In one of the scenario, my current is becoming drift dominant. So somehow, sir, I am able to control the current just by changing the biasing. And this is what you wanted. In electronics, what we want to be controlling, not controlling for a particular device, right? Or a particular circuitry. Like if I change my input, based on the input, things in my circuitry should change. This is what I want to make. As an electronics engineer, this would be my target, that if I only change the supply, my things should be changing, my output should be changing. So if I am only interchanging the supply, like let's just say here I am applying 5 volt and here I am applying minus 5 volt, right? You are not even changing the battery. What you are doing, first you are applying 5 volt, here you are applying minus 5 volt. So when you applied 5 volt, your current was drift dominant. When you are applying minus 5 volt, your current was diffusion dominant. So basic idea I am getting that non-uniformly doped semiconductor can do something for me. When N plus and N can do this much for me, then what will PN would do for me? And from here the concept of PN junction came into action. Because here very lesser concentration gradient is there, no? But in PN a lot of concentration gradient would be there. One side is P. That means here number of holes will be 10 to the power 16, but number of electrons would be 4, 10 to the power 4. And here number of electrons will be 10 to the power 16, but number of holes will be 10 to the power 4. So concentration gradient is very high. Concentration gradient is very high. So if in N plus and N, what was the scenario? So 10 to the power 16 electrons here, 10 to the power 11 electrons here. So concentration gradient is not that high. If I want to make the highest concentration gradient, what I need to do? One side you take P, one side you take N, and you control the current. And from here, the concept of PN junction came into action. And from PN junction, we made diode. Are you able to connect the dots now? If I started from PN junction directly, it would make zero sense. You wouldn't even understand what we are doing. But now you have the target that, sir, what we are actually doing, what was our target? Our target was to become controlling. First scenario we studied due to doping. But if I am doping, that means I need to change the complete device only. So again and again, I cannot change the device, right? If someone says that I want this feature in my phone, and now some guy came into action and he said that I want some different feature. So what you will say? Change the mobile. This is one scenario that you can change the mobile. Second scenario would be the same company. He will include more features. So similar scenario we are doing, that we will take that kind of semiconductor. Which kind of semiconductor we are going to take? That kind of semiconductor we are going to take. If I only change my input with respect to the change in the input, he will be able to change the output as well. But if I was taking uniformly doped semiconductor, then this was not happening for me. Then I took non-uniformly doped semiconductor, N plus, and then this was happening for me. And then I thought that if this much of concentration gradient is doing this much of magic, then what if I take PN junction? So that would make more magic, right? So that's why we studied all this scenario with respect to N plus and N junction. Although we will write down the summary, we will summarize the whole points. So comparing all three scenarios, these were the scenarios. First was the scenario, there was no bias applied, then this bias was applied, and then opposite bias was applied. So here if I say, sir, why this is VBI? Why this is built-in potential? Because if N plus and N was there, no? Like when they were different from each other, at that time, this was the scenario. And when they came into action, when they came together, what really happened? This bending took place, no? This bending took place. Previously, there was no bending. This is known as bending. This was flat, EC was flat, EC was flat, EFN was flat, everything was flat. When they came together, I know that EF would be flat only because there is no current. But some bending took place in EC. Why this bending took place? Because there was some built-in potential. So this particular scenario, this particular height, what this would represent? Sir, this would represent QVBI, not VBI. Why QVBI? Because sir, VBI would be having a unit of volt and charge can have the unit of, so this would be electron volt. So this is energy, no? From energy to voltage, how we would go? Sir, let's just say my energy is KT. If I want to write down voltage, what I would do? KT by Q. That would be my VT. So here, instead of writing VBI, I should write down QVBI. Are you able to understand this point? Very simple thing. Voltage, charge. Voltage into charge. Energy is equals to E equals to QV. So voltage multiplied with charge, that would be energy. So if I am making the diagram of energy, here better I should write down QVBI, not VBI only. Okay. So what I would write down? VBI. So this band bending took place because of what? This band bending took place because of the built-in potential. So this would represent your built-in potential. So this is your built-in potential. So here QVBI multiply with Q, multiply with Q. Okay. So this would be your QVBI. When you applied this bias, then this was your VBI already, right? Here what really happened? Sir, VBI plus VB. Again, like arrow sign should not be made. Better would be I should represent it by plus minus, right? Because arrow sign we make for electric field. For the potential, we always make plus minus sign. Here what really happened? Sir, VBI was there, but it was opposing each other. So this was the scenario of QVBI. Now this has become QVBI minus VB. And here you can see that sir, diffusion, it would be diffusion dominant. So here sir, diffusion is more. What about this one? Sir, this particular, what do we call it? This particular height has been increased now. Previously it was QVBI, but now this has become QVBI plus VB. So barrier has increased now. Barrier has increased, that means diffusion would be less, but drift would be more. So this has become drift dominant. Okay. In both of the condition, there would be current. EF and I should not write down. EF I am writing now. And here also EF I am writing now. Okay. And we can see that sir, we are able to control the current just by changing the polarity. Here I am applying 5 volt, here I am applying minus 5 volt. Or you can say sir, this is 5 volt, this is minus 5 volt. It would be relative, no? Someone says this is 5 volt, then he would say this is minus 5 volt. If someone is saying this is 5 volt, then this would be minus 5 volt, right? So here drift is more, diffusion is more. Here there is no current. Here there is drift equals to diffusion. Okay. Now let's find out the expression of this built-in potential. We have already found out the expression of built-in potential, but using the mathematics. Now using the diagram only, I will find out the built-in potential. So what is the meaning of built-in potential? When there is no external bias, or you can say open circuit, when there is no external bias, then what is the potential that has been set up inside the semiconductor? That is known as built-in potential. Okay. When the semiconductor is under equilibrium, when the semiconductor is under equilibrium without any external bias, no external bias means equilibrium condition only. When the semiconductor is under equilibrium, then what kind of potential has been built up? That is known as built-in potential. So what really happened? When they were not in contact before junction, this was the scenario. Again, yaar, this EC is near to, like this EC and this EC is same only, right? Both are same. This EV and this EV is also same because they are the same material. So I am using the same material. So EC, 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 EFN, EFN, this was the scenario. But what really happened? As they came into action, equilibrium will be maintained. Equilibrium will be maintained. That means current would be 0. That means this has to be close to each other. Both has to be close to each other. That means what really happened? This part came downward and this part came upward. So this was the scenario that we were getting. And sir, this was representing my QVBI. QVBI. Now look at the diagram carefully. Just let me know what is the value of this one. Let's just say here I am saying that my doping is ND1. Okay. And here I am saying that doping is ND2. And you know that ND1 is much more than ND2. So what will be this particular width? Sir, it would be KT ln ND1 by Ni. And what do you think, what will be this particular width? Sir, it would be KT ln ND2 by Ni. Now those who are smart enough, or those who are putting good amount of concentration, just let me know, can I write down QVBI equals to KT ln ND by Ni, ND1 by Ni minus KT ln ND2 by Ni. How did I write it down? Just let us say this guy is not moving, only this guy is moving. Okay, this is what I am saying. Now this EFN has to reach to this EFN plus. EFN has to reach to the level of EFN plus. So how much distance this EFN needs to travel? EFN needs to reach to EFN plus, right? EFN, I am saying that EFN plus is not moving, only EFN is moving. So EFN want to go to EFN plus. That means EFN should cover this much of distance. And what is this distance? So this distance is equal to KT ln ND by Ni. EFI would be at the same place. EFN wants to go to EFN plus. Then how much EFN need to walk? Equals to the built-in potential. Built-in potential multiplied with the charge. So built-in potential multiplied with Q. Or you can say, sir, this distance KT ln ND1 by Ni minus this distance, like already it is there at this particular point, it needs to go for, sir, KT ln ND1 by Ni minus KT ln ND2 by Ni. So that would be equals to QVBI. Is that clear? Without mathematics we are doing, with the mathematics we have already done. And there also I told you formula will be VT ln higher concentration. There we used to write down in terms of N plus and N. So higher concentration divided by lower concentration. Then I told you this will be your built-in potential. But now with respect to energy band diagram as well, we are understanding what we are doing. This guy will actually come downward and this guy will actually come upward. So from here it will be tough to understand, but what I am saying, let's just say this guy remains as it is, but this guy goes upward. So how much distance it needs to walk? How much distance this needs to walk? So this needs to walk for KT ln ND1 by Ni minus KT ln ND2 by Ni. So your QVBI would come out to be KT ln, you can see that, sir, this is ln A minus ln B, so that would be ln A by B. So sir, simply it would come out to be ND1 divided by ND2. And sir, I can take this Q downward. So this will be the scenario I will be getting. So this is my built-in potential. Higher concentration divided by lower concentration. What is Q, KT by Q? That would be equal to VT at the room temperature, right? What is KT by Q? KT by Q is VT only, right? VT is equal to KT by Q. And what is the value of VT? Sir, 26 millivolt at room temperature at 300 Kelvin, right? All these things you already know, right? So V built in equals to VT K ln ND1 by ND2. Higher concentration divided by lower concentration. Okay, so by the energy band diagram, we have understood the mathematics as well, right? So let's solve the question. This has been asked in GATE examination only. N plus and N silicon device is fabricated with uniform non-degenerate doping concentration ND1, ND2 is given considering N plus and N region respectively. At the temperature T, assume complete impurity ionization. What is the meaning of complete impurity ionization? That means I am doping 10 to the power 18, all are becoming electrons. I am doping 10 to the power 15, all are becoming electrons as well, right? So this is the meaning of uniform doping. Value of Ni is given, you need to find out the built-in potential. So those who did not study in a good manner, what they would do? They would apply the concept of PN junction. In PN junction, the same formula would come out to be KT ln NAND by Ni square. Okay. So they would multiply both of them divided by Ni square, they would mess it up. But forget about all these things. I know that what kind of junction I am making, N plus N. Higher concentration divided by lower concentration. N plus N. There is no P, right? So what will be my built-in potential? That would be KT ln higher concentration divided by lower concentration. So they have given the value of VT, that is 25 millivolt ln 10 to the power 3. You will get the answer. Okay. Similar kind of question was asked for P plus and PA junction as well. So whatever that we studied, we have studied for N plus, right? Whatever that we studied for N type silicon. We can study it for N type, we can study it for P type semiconductor as well. So now this is the question that is coming on P type semiconductor. So what do you think, what will be the answer? Answer would remain the same only, no? Vt ln higher concentration divided by the lower concentration. So in 2017 it came for N type, then in 2018 it came for P type. So higher concentration divided by the lower concentration. Just make sure that this is also concentration of P and this is also concentration of P. Okay, just make sure this is the concentration of P and this is also a concentration of hole. Let's just say here they would have given 10 to the power 3 concentration of electrons they have given. They could have mentioned that I am having concentration of electrons, but here whole concentration divided by whole concentration, whole concentration divided by whole concentration, electron concentration divided by electron concentration, electron concentration divided by electron concentration. So always the same concentration I need to divide, right? So Vt ln 10 to the power 2. So 25 only let's take. So that will be the answer you will be getting. Okay, so you can get the answer. I will simply pause the video and then we will start PN junction. Now PN junction will simply be a cakewalk for you. All the formula, everything you will derive, built-in potential you can calculate and you will get your answer. So 25 millivolt ln 10 to the power 3, 25 millivolt ln 10 to the power 2. Both has been asked in gate examination only. Okay, so they are gate question only. So I hope you have understood the whole scenario of a non-uniformly doped semiconductor. So the first half of this video was completely dedicated to non-uniform semiconductors. Sir, why you spent so much of time? I hope now you guys are able to appreciate why I spent so much of time. As of now, we are not able to appreciate. Then when we study PN junction, at that time you would be able to appreciate that, sir, why you spent so much of time. Now PN junction would be completely a cakewalk. Along with that, I wanted to make you understand that, sir, why we are studying PN junction suddenly. Previously P type semiconductor, then N type semiconductor, then sir non-uniformly doped P type semiconductor, sir non-uniform doped N type semiconductor. We studied so much of physics. Suddenly, sir, why do we want to make PN junction? Because I want to be controlling. Okay, I want to control the current. Control the current I could have done with respect to doping, but I don't want that. What I want to control with respect to the applied input, my current should change. So I know that in one condition it is coming drift dominant, in other condition it is coming diffusion dominant. Don't mug it up. Okay, nothing you need to mug up here. I hope you will not be doing that, sir. If I am applying the electric field in this direction, then it would be diffusion dominant. No. Don't remember anything. If I want you to remember anything, that means that will be written in conclusion. But as of now, we are not writing down any conclusion. That means you don't need to remember anything. You need to have the tendency to analyze. Also, when we studied in basic semiconductor physics, we studied this kind of diagram, which kind of diagram, this kind of diagram, but they were not completely correct. The actual scenario would be this. As of now, in this particular scenario, we did not talk much about electric field. But now what we would see, we will be talking about electric field as well in PN junction. So in PN junction, we will talk about electric field as well. Okay, and that would make you realize that maximum electric field will be happening at the junction only. Intuitively as well, you can say why maximum electric field will be at the junction. Because at the junction, these electrons will feel the maximum concentration gradient. These holes will feel the maximum concentration gradient. And if you are feeling maximum concentration gradient, that means maximum electric field would be set up at the junction only, right? Okay, so all this scenario we are going to discuss. So in this video we will understand PN junction under equilibrium only. We are not going to apply any bias. Okay, although for N plus and N we have given the bias as well. But in this particular video we will not apply any bias. PN junction would be under equilibrium. From next video onwards we will start applying some bias. Okay, so let me take a break and drink some water. You should also drink some water and revise everything that we have studied. You can get the answer of these guys, whatever it is, you can get the answer and revise everything. Just important part was this one, that I am able to increase the drift current here, I am able to increase the diffusion current here. Okay, then yeah, let's meet in the next lecture. Sorry, not in next lecture, in this lecture only, but we'll take some break and then we will come back.